Rajan, the recording is it started?
Yes, sir, it is started.
Okay. And slides are also visible.
No, sir, not. No.
Okay. So there is some issue. Let me see. Now?
Sir, now it is visible. It is visible now. Yes.
Okay. Okay. So let's begin with this process synchronization. As you may recall that we have discussed in our introduction lectures, the concept of race condition, synchronization, and concurrency. We have touched upon these three issues. And then I've discussed about interleaved concurrency and overlapped concurrency. So interleaved you will experience in uniprocessor systems, and overlapped concurrency would be experienced in multiprocessor or multi-core systems. So let me again describe these three things. Uh, First of all, let us take this concurrency issue and let's see whether we'll be able to understand this or not. So what I'm saying, I told you that there are two types of concurrency. One is interleaved and other is overlapped. Now, there is a whole series, multi-programming, where many processes can be in main memory and can compete for the processor, led to concurrency, which led to problem of synchronization, which is our topic today and coming lectures, and which led to when you try to solve multi-programming, you are in concurrency. When you try to solve concurrency, you led to synchronization. When you try to solve synchronization, it will lead to starvation or deadlock. So this is the whole series of events. So you started with uni-programming model, then you went to multi-programming, and nowadays we are not even multi-programming, we are talking about time sharing and multitasking, which will lead to issue of concurrency, which progresses to synchronization problem. And when you solve synchronization, if you're not vigilant enough, it will lead to starvation or deadlock. So this whole series we'll be studying in this module. So when I say that there is a single processor at a time, only one process can execute. So this is a very popular confusion that only one processor is there. If there is only one processor, how can we think of concurrency? Because there is a thought process that concurrency means two processes or two things are happening at the same time. Now, why we will experience concurrency even in single processor? Let me explain this. Suppose there are two processes P1 and P2. You people haven't worked upon single processor system. In our time, we used to have single uniprocessor systems, and we have experienced. Suppose P1 and P2 are there. So what will happen? P1 will execute So P1 has started execution. So in time, P1 has executed for, suppose this is our time axis, P1 has executed for some time. After some time, P1 will leave the CPU by any reason, due to timer interrupt, if it is a time sharing system, or due to IO. P1 will leave and P2 will execute. So let's see, let's say now P2 is executing. So as you can visualize that both P1 and P2 are not executing at the same time. Then how we can think of concurrency? That is the question. How we can even say that these are two concurrent processes? Anybody can answer this? Anybody? Yeah, Aman Singh,
Yes, sir.
you got the question?
Yes, I got it. Means why these two processes are concurrent.
If they are not going to execute at the same time because we have only one
One
processor.
process.
Our execution unit is only one CPU is there, one processor is there.
So maybe because they are in queue at the same time.
Now let's see the behavior. Now if I say that, suppose this process P1 is writing some data into this linked list. So P1 is traversing the linked list, and then at any node it is trying to write the data. But before it can write the data, P1 is switched out and P2 got the chance. Now P2 is a process which wants to delete a node from the linked list. So if you see carefully, what would be the effect of these two processes on the linked list? In this case, where there is one processor. Now, if I take this overlapped one, in overlapped, what can happen? If I assume there are two processors, P1 can be executing on CPU 1 and P2 can be executing on CPU 2. And then what can happen? P1 and P2, if this is a time scale, are executing at the same time. Now P1 is traversing and writing on linked list. P2 is deleting a node from the linked list. Just answer me one thing. Are you getting the same overall effect in both cases? Or same problem in both cases? Aman?
Yes, sir. We may get the same problem that the process P2 may act earlier than the P1, and it may delete some node which we are going means which P1 was going to overwrite. So that problem can occur in both the cases.
So, means whether there is one processor or multiple processor, the concurrency issue is there because even if there is a one processor, both processes have started execution and they are in race to get the linked list. Yes or no?
Yes, sir.
And same thing is happening here. So the overall effect is same, which is reminiscent to concurrency. So in one case, it is termed as interleaved concurrency where process cannot execute at the same time. So they are interleaved in time, still concurrent. In another case, they are executing in overlapping manner or they are overlapped in time and obviously they are concurrent. So what I wanted to put forward is there is going to be race condition if there are multiple processes which are active. I'm not saying running. Running means even if there is one processor at a time, only one can run. But there may be many processes who have started execution. They are active and still not finished. So all these processes, whenever they get chance, they can be a part of that race situation. So without loss of generality, the solutions which are going to be discussed further for this concurrency and synchronization, without loss of generality, they are applicable to both environment, whether it's a multiprocessor, multi-core system, or it's a uniprocessor system. That is what is the first issue we need to understand. Any confusion to anybody? Bridgen, is it okay?
Yes, sir. Yes, sir. Okay.
Okay. Now let's move ahead. What are the design issues? So in any modern operating system or any modern system, you'll find these situations. Communication among processes, where processes need to communicate to each other. We have already discussed, and in your programming tools lab, you might be doing this using pipes, named pipes and all, where processes are communicating with each other. Resources are going to be shared because there would be more number of process and less number of resources. The biggest resource is CPU. Even if you have an octa-core processor, 8 processor, still your number of process may be more than 800 at any given time. So there would be a fight for CPU, there would be a fight for printer, there would be a fight for memory. So resources are going to be shared. There has to be proper synchronization of multiple processes, as we have seen just now, the problem of linked list. that if they are not synchronized properly and if there is no arbitrator in between, you may lead to an inconsistent state of data. And then you have to allocate processor time equally and fairly, depending upon, as we have seen, the priority of the process. So because we need to do these things, what are the issues which are going to arise? Not only in multiprocessing and distributed processing environment, but even in single processor multiprogramming system. We have seen this. So even if it is a single processor multiprogramming system, the same issues will come. And in multiprocessing and distributed processing environment, in any case, these issues are going to be there where there is a simultaneous execution of multiple processes. What is the context? In nowadays systems, there are multiple applications. And we follow multiprogramming or multitasking, which leads to dynamically sharing of processing time among number of active applications. Because you want to provide better response time and you want to, as we have seen, the goals of CPU scheduling is to utilize CPU as much as possible. You have to reduce the idle time of CPU. So you keep on pushing number of processes which can be active at any given time. And not only that, if you talk about any big application like Microsoft Word or any other application, these applications themselves are set of concurrent processes. Like your Microsoft Word, when you are typing anything, so many processes are working together. And suppose you are underlining at the same time you are typing, or you have made italic something and you at the same time you are typing. So typing one process and underlining another process, and there can be another examples also. So if you talk about nowadays modern applications, they are themselves are set of some concurrent process. And the biggest software which is running on your system is operating system, which is implemented as set of process or threads. We'll be coming back to threads, don't worry. At this moment, you just assume that thread is nothing but a type of a process. So our concurrency is going to be there. You cannot have a one big monolithic application. You have to have application which is set of some concurrent process which may need to communicate to each other. This is going to be there. Concurrency is going to be there. Challenges. Biggest is global resources, printers and all, memory locations, data structures, databases. Point. Aman, have you ever thought about this railway reservation system?
Yes, I means I have gone through that.
Have you ever realized that what is the problem, biggest problem in railway reservation system, which they have handled amicably?
Which they have handled.
Yeah, they've already handled it. Don't talk about those other problems. Reservation nahi hota hai and all that. I'm talking about the technical perspective. Any seat
Yes, sir.
in any train, there is a race among different fellows who are trying to reserve that seat sitting at different geographical locations, working on multiple processors, and it should not happen that a seat is going to be allocated to more than one at any given time. Got the problem?
Yes, sir.
So what is this? The seat number, the seat which is vacant, is globally available to many processes, and they are performing reads and writes. So they are booking, or if you are canceling a ticket, that is getting available to everybody. If you are booked the ticket, you are writing that your name should be written into that entry that this ticket for this date has been booked for some fellow. So this is the biggest challenge, because number of resources would always be less than number of fellows who are in race for these resources. Management of allocation of resources. This is most important. Suppose a process is there which is granted a particular input output channel, and it is trying to write into that input output channel, or trying to use that input output channel, or about to use that input output channel, but that process is switched out before using that channel. So if you have been allocated a resource, you should use it, or you should lock it so that nobody else can use it until unless you are done with that. So this management is a biggest challenge of resources. And above all, when these type of programs, concurrent programs, are written for management of access of resources, for sharing of global resources, when you write these kind of programs, we'll be writing some programs like this. Results are not deterministic and reproducible, because it is very difficult to analyze the execution order of the instruction of different processes. And it is also very difficult to analyze the relative speed of the processes when they are executing on CPU. So because you are not able to reproduce the trace again, it is very difficult to find out the bugs and errors in this type of programming. So these are the three major challenges in concurrency. Let's take a simple example. This is a simple function, echo function, where you are taking a character from keyboard and assigning it to chin variable. Then you are assigning this chin variable to chout, and then you are printing that character to monitor. Now this is one simple program may be used by operating system. Suppose it is maybe getting used by operating system when you type something on keyboard. So it's a simple thing. You take something from standard input and then display it on standard output. So there is a simple program which like this can do this thing. And this simple program is going to be utilized by all the processes. Suppose there are process P1 and process P2, and they want to execute this simple program. P1 also want to take some input from keyboard and want to display it. P2 also wants to do this thing. Now, if there is no control, what can happen? That P1 has started using this code. After it has executed one line, P1 is switched out. P2 got the chance. P2 executed this line. Considering if there are two CPUs, suppose P1 and P2 are executing this instruction in on their own CPUs. It's a shared code and shared variables. And then P1 is executing this and P2 is executing this. What is the problem? What is the issue here? Anybody? Yes, Anukul Jaiswal. Hrithik Singhal. Megha Gupta.
Yes, sir.
Yes. Are you seeing any problem here?
Yes, sir. एक ही वेरिएबल सर दोनों जो प्रोसेसेस हैं वो एक ही टाइम पर वेरिएबल्स एक ही वेरिएबल जो शेयर्ड वेरिएबल्स हैं यूज़ कर रहे हैं तो ये प्रॉब्लम आएगी कि मतलब कौन सा पहले यूज़ करेगा प्रोसेस 1 या प्रोसेस 2 और मतलब और लॉक भी करना पड़ेगा मतलब एक ही वेरिएबल को दोनों कैसे एक ही टाइम पे एक्सेस कर सकते हैं ये
नहीं, अगर कर रहे हैं तो क्या होगा? Suppose P1 took A from the keyboard. So when P1 is suppose P1 when P1 was executing, P1 got A. Somebody typed A from the keyboard, character A. So CHN would be having A. Then P1 is switched out. P2 executed. Suppose P2 gets B. What will happen?
Firstly, sir, key is lock करता है.
Don't think about locking right now.
तो सर B टाइप किया राइट P2 ने तो B
फाइनली B आ जाएगा.
हाँ.
और जब पुट कैरेक्टर करेंगे पुट कैरेक्टर तो इन बोथ प्रोसेस P प्रिंट होगा फाइनली. यस और नो?
हाँ यस सर.
Fine. So this is a normal situation and this is going to be experienced both in single and multiple processor system.
Yes sir.
Even if there is a single processor, this situation can occur.
Yes,
P1
sir.
gets a chance, then P2 gets a chance, then again P1 gets a chance, P2 gets a chance. If switching is happening back and forth between P1 and P2, you will not be able to get the correct answer.
Yes.
Solution is to lock the shared global resource while a process is utilizing that. So what is the solution? That lock this whole code. Okay. So if one process is using until and unless that process unlocks this whole function, no other process can use it. We know the solution is locking, but that is easier said than done. We'll be seeing this particular issue in this module. What are the OS concerns? Has to keep track of active processes using our P table, which is list of proc structures. It has to allocate and deallocate resources. Resources can be processor time, memory, files, IO devices. And it has to protect data and resources. It should not happen that anybody is writing and data is becoming inconsistent. And the most important thing is whatever solution you are proposing to handle the issue we have discussed just in the previous slide, whatever solutions you are proposing, result of process must be independent of the speed of execution of other concurrent process which are in race. So there may be 5 or 10 processes which are having race for a resource. It may so happen that process P2 executes 20 times and P1 executes 1 time in a unit time in a given time period. So result of overall solution must be independent of relative speed of execution of other concurrent process. This is most important. So whatever solution you are proposing, you need to check whether this particular condition is taken care of or not. What kind of interactions can be there among processes? Processes may be completely unaware of each other, but they may be competing for the resources. So it's a kind of very implicit interaction. So in an apartment building, there are many fellows who are residing. They may be unaware of each other, they don't know each other, but still they are somehow related because they are using the same lift or elevator. And there is a competition for that lift. So they may be completely unaware of each other, but still there is a little bit of interaction due to the resource which is getting shared. Process indirectly aware of each other. Like we have taken one example of linked list because they are sharing the common object. That can be a linked list or a printer. So they are indirectly aware. They are not actually working together, but they are cooperating in sharing a common object. Processes directly aware of each other. This is where processes know each other and do message passing, do communication to synchronize each other. So in these all 3 type of interactions, we need to provide synchronization solution where there is a direct communication, where there is a indirect awareness because they are cooperating to share a common object, and where they are completely unaware but still they want to compete for the resource. All these type of interaction we have to think about synchronization solution. Competition among processes. Execution of one process may affect the behavior of competing process. If 2 processes wish to access the same non-shareable resource, just take that elevator example again. And if I say there is a constraint that at a time only one fellow can travel into that lift or elevator, then this particular situation arises. It's a non-shareable resource. At a time only one process can use that. And if 2 fellows want to access the same non-shareable resource, obviously one process would be allocated and another will have to wait. So process is ready to execute, but because it is not able to get the resource, it has to wait for other. Here non-shareable means can't be used simultaneously by different processes. There may be a situation and you may realize the process which is waiting might never get access to that resource and never terminate. Just waiting for that resource, waiting for that resource, waiting for that resource. Because until unless it uses that resource, it cannot move ahead in its code and may never terminate. We will be seeing this type of situation. And you might have also seen how many of you have experienced sometime when you are watching movies, sometime your movie get stuck. Aman?
Yes, sir.
You have experienced this, that you are watching movie from a downloaded video file and your movie is getting stuck.
No, sir. Means not downloaded one.
You haven't experienced? Oh.
Not yet, sir.
Achha, how many time in your life actually you have used Control or Delete? Or how many time you have opened your task manager to terminate a process?
So means I have opened Task Manager few times.
Hmm. But you have never killed any process.
No, sir.
Okay. Brajendra?
Yes, sir, I did that.
Many a time this happens that your system gets hanged because there is some process which is not able to get resource and it is already using lots of computing resources. But because it is not able to get the resource it needs, it is hanged. I don't know whether you have seen those times or not, Brajen. Normally, when we used to watch movies using our CDs and DVDs, this used to happen. So there is some data which is we are not able to read, and that resource we are not getting, and due to that, that process gets blocked. And the process which is getting blocked, it have already utilized so many user resources because it's a movie file, it is using coder, decoder, all the process. So your system get hang. And then you use control or delete to kill that culprit process so that your system can again come up. What Aman used to do, maybe hard shutdown. Yes, Aman? Hang ho gaya to.
Yes, sir.
So before doing hard shutdown, if your system is not performing, you need to check uh, whether any process is culprit. You can see it if I open the task manager. Goodness. You can see here the list of process and the amount of memory and CPU they are utilizing. If you get any process which is utilizing more memory and more CPU more than the normal utilization, you can go there and kill the process. If you see here right now, MS Team is using lots of memory. And the next is these 13 different tabs of Google Chrome is using lots of memory. Okay. So in Linux also you can do this thing. You can give the kill command and the process ID and that process can be killed. Anyway. So what is needed when there is competition among process? What is needed? We need mutual exclusion. And which is achieved using critical section, which are piece of code to access critical resources. with a rider that only one process at a time is allowed in its critical section. For example, only one process at a time is allowed to send command to a printer. So let's move to the whiteboard and I'll try to explain this. So in our network lab here, we have one network printer which is connected to the LAN of our lab. It's a printer. Now, anybody who has installed this network printer, any PC who has installed this network printer can fire a print request. Now, if there is no control, what can happen that suppose this system 1 has fired 10 pages, system 2 has fired 5 pages, its fourth page was getting printed and system 2 has fired 5 pages. So it will be a problematic situation. So what is happening to access the printer? Everybody has to access a piece of code. Which can provide access to the printer. So process P1, P2, P3, P4, everybody will make a call to this piece of code or function to get their files printed on printer. Now what we want that if P1 is using printer, this situation should be mutually exclusive. Means if P1 is printing, nobody else can print. Anybody else can get a chance only when P1 declares that I'm done with my printing job. So here this piece of code is declared as critical section. And every process has to execute this critical section. And what is ensured is that at a time only one process can be there in its critical section. That has to be ensured to provide mutual exclusion. This is what is mentioned in that slide. Only one process at a time is allowed in its critical section. But what may be the situation, as we will see later on? This may result to two another problems, deadlock or starvation. If you want to provide mutual exclusion, it may lead to starvation. If you haven't taken care of fairness, some processes may starve to get the printer, or there may be a situation which can lead to deadlock. We'll be coming to that. When you processes are, this is competition among process where they are not aware of each other process. When you processes are cooperating, indirectly unaware, indirectly aware, they are cooperating by sharing. Then process use and update shared data such as shared variables, files, and databases. Databases, I have given one example of railway reservation. Shared variables is that linked list structure. Files, when you are trying to write and read into the files. Writing must be mutually exclusive. At a time, only one can write, and until unless writing is done, nobody can read or write. And here also critical sections are used to provide mutual exclusion on data. In the first two cases, each process had its own isolated environment, does not actually communicate with the other process. Interaction among processes are indirect. In both cases, there is a sharing. In the case of competition, they are sharing without being aware of other process. In the case of cooperation, they are sharing values, even if they are not explicitly aware of other process, but they are aware of the need to maintain the data integrity. This is most important. The difference between two cases. In case of competition, they are completely unaware about each other. They are sharing the resources, but they are completely unaware about each other. In second case, where they are cooperating by writing into shared variables and files and shared data, they are not explicitly aware, but still they need to be aware of the need to maintain data integrity. Let's take one example and let's see whether we can do it or not. What I'm saying, there are two variables, A and B. And both of these variables are shared between P1 and P2. Next, I'm saying that accessing of these two variables is mutually exclusive. Means when one process P1 is accessing A, P2 cannot access it. When process P1 is accessing B, P2 cannot access it. There is an integrity constraint that after operation, A should be equal to B. Now what P1 is doing, P1 is doing A equal to A plus 1, B equal to B plus 1. What P2 is doing, B equal to 2 into B and A equal to 2 into A. When P1 is accessing A, P2 cannot access. When P2 is accessing B, P1 cannot access B. So mutual exclusion is there. They know that they are sharing variable, they are indirectly aware of each other. So we need to provide mutual exclusion over shared variables that we have done. Suppose we have done. But there is a constraint, overall constraint, which suggests that after everything, A should be equal to B. My question is, in this situation, if P1 and P2 are executing, is this constraint be maintained? That's the question. Anybody can answer. Yes, Rajiv Ranjan. Saksham Saxena. Shivam Chaudhary. Deepak Gangwar. Arun Nagar. Anurag Upadhyay. Anjali Bhatia. Anchal Tiwari.
Yes, sir.
बताओ बेटे.
Am I audible?
Yes.
So A equal to B, sir, how will it be maintained? I mean, sir, if one process has the access to one variable and it can't be accessed by the other one.
Mm-hmm.
So, sir, if one process changes it,
Then
so sir, then how will it be maintained? Like A is equal to B, I think so
at
it
a
can't
at
be
a,
maintained.
at the same time, these two
Yes, sir.
processes cannot access A.
Yes, sir.
Suppose P1 does, suppose A is initialized to 1, P1 executes A equal to A plus
A
1,
plus 1,
it will be 2,
2. Yes, sir.
then P2 does 2 into A, suppose P2 executes afterwards, it will be
So now it
2,
should be
4,
4. Yes, sir.
4, so A is 4. So A में तो कोई problem नहीं है.
Yes, sir. Sir, but B, so what about B?
So let's see B.
Yes, sir.
B equal to, suppose B is also initialized to 1 because both has to be equal.
Equal, yes, sir.
Just wait. नितिन क्लास में है अभी. So B is 1.
So if one process is acting with A, can the other process act with B, sir? If
That's the question here.
yes, sir. So because then it can be maintained equally.
That's the question here. I'm saying A cannot be accessed at the same time by both processes. But if P1 is accessing A,
Yes, sir.
P2 can access
B,
B.
yes, sir. That's what I'm saying. Yes, sir.
So if P1 has accessed A equal to 2, done. Now what P2 has done, P2 has accessed B. If B is also initialized to 1, then it would be 2 into 1 equal to
2.
2. Now suppose P1 accesses B. If I say that this is the first instruction in overall execution sequence, this is the second which will be executed, that is possible. P1 execute किया, switch हो गया. P2 ने execute किया, second ये. P3 ने execute किया. P1 execute किया, third instruction ये. And fourth will be this. Now, so first instruction is this. This is first, A equal to 2. Okay.
Yes, sir.
Second instruction, B equal to 2. Second instruction. Third would be B equal to B plus 1, which is 2 plus 1 equal to 3. This is third instruction which is executed. And then you move to A equal to 2 into A. What is A now? 2. So 2
4.
into 2, 4. So after the overall execution, this is fourth instruction. This constraint is not honored.
Yes, sir.
So even if you are having mutual exclusion over shared variables, your data integrity constraints may not be honored, may not be maintained, even if you are having mutual exclusion. So you know that processes are sharing variable, and the rule is to, if there is a shared variable, you should protect it and you should make their access mutually exclusive. So we have done that, but still we are not able to maintain the data integrity constraint. So what is the solution, Anchal? Yes, Achal Tiwari. What is the solution?
So I'm not sure. So we have to maintain the condition as well. So sir, maybe the instructions should be, but sir, how will we able to manage all the instructions? Keeping
Now
them mutually exclusive.
in
Yes,
this
sir.
case, if I declare A equal to A plus 1,
Yes, sir. Maybe some change in the instructions.
B equal to B plus 1 as one block of critical section,
Oh, yes, sir.
means if P1 is executing this, it has to execute both together.
Together. Yes, sir.
Means now if it is in one block, B is also blocked, no?
Mm.
So if P1 is executing first instruction, P2 cannot use B here because it is in this critical section block. B is also blocked. Got the point?
Yes, sir.
So P2 will wait. Now P1 will execute both of these instructions, and then both of the variable would be free. Now suppose we do this thing. A equal to A plus 1 and it is 2.
2.
B equal to B plus 1 equal to 2. Done.
Yes, sir. And then.
And now you do this. 4, 4. Got the point?
Yes. Yes,
So
sir.
so you have to be very careful while writing programs of these types, that if there is a shared resource or shared variable, you cannot be just bullheaded that, okay, if it's a shared variable, just lock it. No, you have to see the serializability also of the other instructions. Got the point? So that's what is mentioned in this slide, that each process is not explicitly aware of the other process, but it is aware of the need to maintain the data integrity. The third type of cooperation is by communication. Processes cooperate by communicating. They are participating in a common effort. Mutual exclusion is here is not a control requirement. You may want it, you may not want it. But this communication provides a way to synchronize, to coordinate the various activities, which can be realized by message passing. In different operating systems, some primitives are provided by OS kernel. Some programming languages also provides these primitives where processes can send messages to each other. But they may lead to deadlock or starvation. It may so happen that I'm waiting for a message from another process. That process is waiting for a message from me. Both are not able to progress because both are waiting for each other. That is a deadlock situation. It may lead to deadlock or starvation. So as we all know, requirement is mutual exclusion. Only one process at a time is allowed in its critical section for a resource. There are certain rules. A process that halts in its non-critical section, if it is halting in critical section or getting killed in its critical section, that's another story. Then no other process will be able to proceed, because before unlocking, after unlocking and before unlocking, if it is killed somehow, then no other process can enter because the resource will be locked forever. But if a process is halting in its non-critical section, this action should not interfere other processes, should not make any effect to other processes. When we are providing mutual exclusion, we have to be very sure that there is no deadlock or starvation. What are the requirements when you provide mutual exclusion? First requirement, a process must not be delayed access to a critical section when the critical section is empty or no other process is using that critical section. If critical section is not getting utilized by any other process, so process who wants to use that critical section should not be delayed. Another point is a process should remain in its critical section for a finite time only so that other can also get chance. And most important, which is given in red, is no assumptions are to be made about relative process speeds or number of process. So if a solution is good for 2 process, it should be good for 100 process and number of process. It should not happen that the relative speed of the process can affect the nature and the behavior of the solution. That should not happen. There are 3 approaches to provide mutual exclusion. The software approach, where there is no programming support, no support from programming language, no library support from programming language, no support from operating system. It is just like you are writing your own codes using your programming. Like in Java, there is a support. If you have Word over Java, there is a synchronized class. You can have synchronization. In Python also there is a support. But if you talk about C, there is no support for, or even C++, there is no support from programming language to provide mutual exclusion. Some operating system provide constructs to get some system calls to achieve mutual exclusion. But in software approaches, no such support is available. And that's why they are prone to high processing overhead and lots of bugs. So we'll first of all see the software approaches or our programming approaches. In some hardwares, there are special purpose machine instructions which can reduce the overhead, but they are unattractive as a general purpose solution. Then finally there is operating system or programming language support. So we'll be seeing all these kind of solutions slowly and gradually in coming lectures, starting with software approaches. Then we'll see the machine instruction means hardware is providing you some instruction support. And then finally, we'll be seeing OS or programming language support. So we'll be stopping here. And if there are any questions, you can ask. Otherwise, we can leave. Brijendra, any questions?
सर ये जो कोऑपरेशन बाय कम्युनिकेशन है सर, इसमें म्यूचुअल एक्सक्लूजन का बिना जरूरत के भी सर हो सकता है क्या ये?
ऑब्वियसली
यस, मतलब वो
नीड ही दूसरी है, नीड दूसरी है।
मतलब वो जो
हम पहले ही बता दें, उसको सिग्नल दे दें
समझ गया
कि यार हम जब काम करेंगे तब तुमको सिग्नल दे देंगे, तब तुम चले आना। म्यूचुअल एक्सक्लूजन अपने आप दूसरे तरीके से हो जाता है उसमें, क्योंकि वहाँ मैसेज पासिंग से कोऑपरेशन हो रहा है।
सारे के सारे प्रोसेस अवेयर हैं किसको क्या चाहिए, तो वो पहले डिसाइड कर लेते हैं, अभी मैं यूज करूंगा, बाद में तुम, बाद में तुम।
हाँ, वो आपस में बात करके कुछ अपना स्कीम बना लेंगे, कुछ लॉटरी सिस्टम कर लेंगे या टोकन पास कर देंगे। ठीक है,
ठीक, समझ गए सर।
ठीक,
ओके सर, थैंक यू।
Okay. Any other question from anybody? Okay, if there are no question, then thank you.
Okay, sir. Thank you.
Okay, Brijan. Thank you.